Welcome to this Unit 5 on simple machines. This is one of the units as part of the Grade 9 studies in physics. My name is Dr. Raymond Carty, and I'm going to take you through this unit and look at some of the theories, concepts, and also ideas related to simple machines. So after completing this unit, students should be able to do the following. You should be able to explain the purposes of machines, as well as list the types of simple machines. You should also be able to identify whether machines are classified as force multipliers, speed multipliers, or direction changers. You also need to be able to state the following terms: load, effort, load distance, effort distance, work output, work input, mechanical advantage, velocity ratio, and efficiency. In addition, students are also required to be able to do the following. You should be able to derive the expression of efficiency is equal to mechanical advantage divided by the velocity ratio. You should also be able to determine the mechanical advantage, the velocity ratio, and the efficiency of different simple machines. You're also required to be able to develop problem-solving methods for different simple machines, as well as identify applicable areas where simple machines can be applied. Let's begin by looking at some of the physical terms which we have in relation to the topic on simple machines. And the first of these that we're going to look at is the term effort, which is given the symbol E. So what exactly is effort in relation to machines? Well, effort is the force exerted on a machine by external body. So, for example, the force exerted on a machine by you would be classed as an external body, as a human being who's exerting a force. Load, given the symbol L. Well, this is the force applied on the object by the machine. So, if you think about it in terms of what exactly is happening, you would apply an effort, which is the force exerted on the machine by an external body, which could be you, and then that machine applies a force on the object, and that would be the load, and that is given the symbol L. Now, effort distance, what exactly is this? Well, this is usually given a symbol SE. It can be given other symbols, it doesn't really matter, or other labels. But what is important is that when we talk about effort distance, this is the distance moved by the effort. So let's go back to effort and see how it links into load and how load links into effort distance. Again, let's imagine you apply a force on a machine. Then that machine applies a force on an object, and then the distance that the object moves would be called the effort distance. The load distance is the distance moved by the load, and that's given the symbol SL. And again, it's quite easy, hopefully, to understand, because if you think in terms of the load distance, the load distance is going to be the force which is applied onto the object, and as a result of that, the object moves. And so that would then be the distance moved by the load. Now, the work input is really given as the work done by the effort. And we have looked at work done in terms of energy, and we've looked at that in the previous unit. But when we talk about work input, we can actually say that work input is equal to the effort multiplied by the effort distance. This shouldn't be too surprising, because when you think about what we've looked at in the previous unit, when we looked at forces, energy, and power, we know that work done is equal to force multiplied by the distance that the force moves an object. So in many ways, work input, which is very similar to the work done, is going to be equal to the effort, which is equivalent to the force applied, multiplied by the effort distance, which would be equivalent to the distance moved by the object that the force has been applied to. Now, in this context, what we can write is we can say that work input is equal to, and we can write it as W and then IN to signify that it's input, is equal to the effort, and we can call the effort E, or signify it with the letter E, multiplied by the effort distance. And remember here, we actually used SE to represent the effort distance. The work output, well, this is the work done by the machine, in other words, the load. And the work output is again similar to the work input, but as the name implies, it's the output energy, and that's equal to the load multiplied by the load distance. So when we write this, we write it in a similar way to work input, but what we would do is we'd write W out to signify work output, and that's equal to L, the load, and that's multiplied by the distance which is moved by the load. These are some of the physical terms that we're going to use in simple machines. There are other terms which we're going to have a look at in a moment, but these are the first set of terms that you need to know. So what exactly are the purposes of simple machine? Well, simple machines are designed for one or more of the following purposes. They can act as multiplying forces. They can multiply speed or distance. They can also change the direction of a force. Now, no machine can do the following. No machine can multiply both force and distance at the same time. In other words, no machine can actually do this simultaneously. So if we say that a machine can in fact multiply both force and speed at the same time, what we're really doing is we're violating the law of conservation of energy. And this is very important when we look at machines. Now, this will be explained in more detail as we go through the unit, why you cannot multiply both force and distance simultaneously. We'll look at that further on in the unit, but it's important to know that that is a very important rule. Now, in an ideal machine, or a perfect machine, if you'd like to look at it that way, there is no energy loss inside an ideal machine. So in the ideal machine, the perfect machine, the work input is equal to the work output. In other words, the amount of energy that goes into that machine is equal to the total output of energy from that machine. And that would be for a perfect or ideal machine. Now, because work in can be written as the effort times the effort distance, and because work output can be written as the load times the load distance, then these two must be equal to each other. In other words, E times SE is equal to L times SL. Now, when we look at an actual machine, in other words, machines that we find in everyday life, in real situations, then in reality, there is energy loss between any contacting surface, and this can be due to friction. So, for example, you could lose energy, or you can have energy transferred into another form because of friction. And machines that are considered in the presence of friction during their operations, these are known as actual or real machines. And we come across these when we think about, for example, inside a car. There are many different types of machines operating within a car, and these machines are real machines because energy can actually be lost. In other words, transferred from the main form to another form. So in this case, some amount of input work can be lost in the form of heat. As a result, the output work is less than the input work. And so that kind of makes sense, because if the input work goes into a machine and then some of the energy is lost, then it must mean that the output work would be less than the input work. And so what we can say is that in a real machine, the work input is going to be much greater or greater than the work output. And what we can determine from this is what's called the wasted energy. So the wasted energy, the energy that we actually don't particularly need in order to operate the machine, that would be given as the work input subtract the work output, and that would be equal to the wasted energy. So what are the functions of simple machines? So based on what they actually do, in other words, their functions, you can classify machines into 3 specific categories. And these are force multipliers. Now, what is a force multiplier? Well, a force multiplier, these are machines that are really designed to provide a larger output force over a small distance. And this is done by applying a small amount of force, which is the effort, over a large distance. So you can see that the reason why it's called a force multiplier is because you're using a small amount of force, the effort, in order to produce a larger output force. You're multiplying the force from the initial effort force to a much larger load force. So if a machine is a force multiplier, then the load is greater than the effort. And also, the effort distance is going to be greater than the load distance. In other words, L is greater than E, the load is greater than the effort, and the effort distance is going to be greater than the load distance. So this is an example. This diagram is a nice example of a force multiplier. Here we have a gentleman who's applying an effort force at this point. You can see where his hand is. He's going to push down on that, and you can see the distance between the effort force and the point here, which is the fulcrum. You can see that that distance is much longer than the distance between the fulcrum and the point on the load, let's say at the base of the load. So the load now, that is going to be much, much larger when you apply a smaller effort and a larger effort distance compared to a larger load and a smaller load distance. So in other words, this device, this lever, is actually multiplying the force. So that way, you can apply a small amount of force, and that will then produce a larger amount of force in order to lift the object. Let's have a look at what's called speed distance multipliers. Now, these are machines which are engineered to move objects over large distances by applying a large amount of effort through a small distance. Now, there are machines which are designed to move the load in a different direction. And this is different in the direction compared to the effort. So, for example, if we look at this diagram here where we have a pulley system, you can see that by applying an input force downwards, in other words, by pulling on this rope, the pulley rope, you can see that the output force will be moving in the opposite direction. So in other words, this is useful if you want to lift an object upwards. You apply a downward input force, and that results in an output force which moves upwards. So this type of system is called a direction changer. If we want to move the load in a different direction to the effort, then this would be an ideal way of doing it. So if a machine is a perfect direction changer, then what will happen, the total input force will be then transferred to the total output force without any loss of energy. Now, when we talk about pulley systems and when we talk about levers and when we talk about force multipliers and distance multipliers, we need to look at a couple of very important key terms, and these are mechanical advantage, velocity ratio, and the efficiency of a machine. Now, the mechanical advantage, usually written as MA, this is the ratio of the output force, the load, and the input force, the effort. So, in other words, we can write the mechanical advantage as follows. The mechanical advantage is equal to the load divided by the effort. Now, if that mechanical advantage is 1 or 100%, then we can say we have a perfect machine. So there are a number of different types of mechanical advantages. There is the actual mechanical advantage, usually written as AMA, and this really is just the mechanical advantage of the machine in the presence of energy loss which is due to friction. And we can see this in many of the machines that are operating around us. Now, the ideal mechanical advantage, the IMA, well, this is really the mechanical advantage of the ideal machine, where there is no loss of energy. And that would be the perfect machine. Now, the velocity ratio, VR, well, this is the ratio of the distance moved by the effort to the distance moved by the load. And we can represent it in this way. In other words, VR, the velocity ratio, equal to the distance moved by effort divided by the load distance. And we can write that as SE over SL. And if we write it in that way, then that is equal to the ideal mechanical advantage. So in the ideal machine, the actual mechanical advantage is equal to the velocity ratio, which is equal to the ideal mechanical advantage. Another very important key term is efficiency. Now, efficiency is usually written using this symbol here, which looks a little bit like an N, but in terms of the actual definition of efficiency, efficiency can be described as the quantity that is used to determine the effectiveness of the machine. In other words, how effective is the machine in relation to its input effort and the output load. Efficiency is the ratio of useful work, in other words, the work output, to the total energy expended, in other words, the amount of work that's inputted into the machine. Now we can write efficiency in this way. We can say efficiency is equal to the work output divided by the work input. And we can use the symbol for efficiency as a shorthand way of writing efficiency. So we can say it's equal to WO, work output, divided by WIN, work input. And so the percentage efficiency, well, that's just going to be the efficiency multiplied by 100%. Now, you can express efficiency in terms of mechanical advantage and velocity ratio. So how do you do that? Well, you can write efficiency, as we've mentioned, as being the work output divided by the work input. But remember, we can write work input as being the effort multiplied by the effort distance. And similarly, we can write the work output in terms of the load multiplied by the load distance. So if we were to rearrange this in terms of load and load distance, we could write the efficiency as being equal to the load multiplied by the load distance divided by the effort multiplied by the effort distance. Now, the load divided by the effort, we can separate that out and then also have load, or the distance load, or the load distance divided by the effort distance. Now, if you remember the expression for mechanical advantage, that could be written as the load divided by the effort. And also, if you remember, the velocity ratio is written as the effort distance divided by the load distance. Now, you can probably see why load distance over effort distance, well, that would be equal to 1 over the velocity ratio, because we've just inverted load distance and effort distance here. So what we can say is that the efficiency is equal to the mechanical advantage multiplied by 1 divided by the velocity ratio. And that would give us the mechanical advantage divided by the velocity ratio. The mechanical advantage can be expressed as L over E. That's just a shorthand way of writing it. And so what we can say is that 1 over the velocity ratio, or we can write that in a shorthand way as being SL over SE. Therefore, we could write the efficiency in terms of a percentage efficiency. We could just write that as MA over VR multiplied by 100%. So what we've done is we've linked the efficiency, in particular the percentage efficiency, to the mechanical advantage over the velocity ratio. So now let's have a look at an example of a problem that we can actually do based on what we've looked at so far in terms of the concepts. So look at this example here. A simple machine uses 200 newtons force in order to move a 400 newton body through 5 kilometers, while the effort moves through 20 meters in 4 seconds. It's asking you to calculate 4 different things. It's asking you to calculate the mechanical advantage, the velocity ratio, the work input, and the work output. In addition to these 4, the question is also asking you to determine energy waste, the input power, the output power, and the wasted power. There's quite a few different areas in terms of variables that we need to calculate from this example. So we've got quite a few things that we're given and quite a few things that we need to find. So let's just map them all out. So let's go through all of them. What we're given the effort is 200 newtons, we're given the load is 400 newtons, we're given the fact that the load distance is 5 meters, we're given that the effort distance is 20 meters. So given that the time is 4 seconds. So the first thing that we need to determine is the mechanical advantage. So how do we work out the mechanical advantage? Well, that's quite straightforward because by definition, the mechanical advantage is equal to the amount of load divided by the amount of effort. And in our example here, we have a load of 400 newtons and we have an effort of 200 newtons. Therefore, the mechanical advantage is equal to 2.